Okay, so let's start. Oh, yeah. So these are just some codes you don't need to understand. Okay, so I will. So basically, it's chapter 4, and this is so we will introduce some elementary quantum gates, and I was planning that I will cover some decomposition theorem so that we can prove that we. So I will convince you that this two to n unitary can be decomposed by some finite simple unitaries. And this is a very beautiful theory that just built, I think it's 20 to 30 years. Okay, and the quantum circuit model is the model that we are trying to use. Okay, these are just some yeah. Oh, so the goal is that so for this section to tell you that how to deal with unitary meshes. Meshes to and there are continuous unitaries, right? So let's say, imagine that you can do some elementary unitaries. How can you approximate arbitrary unitary to find out? So my question is that how many elementary? So for a classical, you only need one, right? You only need net. So how many of net? Okay. Okay, so we start with the single cubic gate. Right? Let's don't work out with let's forget about the general, right? Let's talk about n to be one. So we know that single cubic is a0 plus b1 or a, or you can do as a vector a b. So all of these are so there are simple unitary upcoding matrices x, y, and z, and algebra and phase is over pi over a, and we will define it. So a single cubic gate has a Pauli x, y, and z. I think everyone knows about this. And there are three of them that will play important in this lecture. So it's one algebra that we already defined in change x into z, and the so-called S gate. So S is just 1, 0, 0, I. And the T is 1, 0, 0, x, 1, 0, I over 4. So you can do S basically T squared. If you square it, you get x, 1, 0, I divided by 2. So we do that. So S is called base gate, T is called pi over 8. And there are some relations that I proved. I think I proved it. So how do I change X to D? Okay. So these are very simple single cubic gates, right? You apply on single cubic. And that definitely you will not generate the two-to n times two-to-n, right? Because there's no entangle for this gate. Okay, so this T is the important gate that we will talk about, the so-called T gate. Okay, so the name so the name is not good, but usually T is also called pi over 8 gate. Even you can take an extra pi over 8 and connect the over face, so you get a 2 pi over 8. So call pi over 8 due to some historical convention. Okay, and some people just refer it to the T gate. All right, so the first question is that okay, so you have some elementary gates, right? You have some elementary single cubic gate. Yeah, I think this is what I already described before. Basically, there's block sphere. Okay, and okay, and you can take this block sphere and okay, you can take the Pauli x, y, and z and do the unitary like rotation along the axis. So I think these are all. I think I proved it. I proved this result before. You can check out videos. If I correctly remember it, you just you take that sine theta I over 2 that minus I sine theta, and you take this as a horizontal. Okay, so if you plug it, you can figure. So these are rotation. Oh, so this is the yeah. So if you take any real unit vector, and then you can define a rotation of theta along this along this vector. And the proof techniques, what okay, so the idea to write down explicitly from formula of this guy just using a squared equals 1 that you can prove it's going to IX. So the proof is that you just kind of expand this guy and it connects all the even and odd power respectively, and you get cosines. Okay, so you can write it down. You can write this unitary rotation matrices. Easy. Okay, so the first so once we have this elementary method, so we can solve one simple question: is that how can I write down general single group unitaries using these unitaries? Right. So in general, we need to solve like 2 to the n times 2 to the n. But let's say solve simple case. We solve n equals to 1. We ask how many? Can I build some? Can I decompose a single cubic unitary into the unitary that I already know? Right. This is the simpler question that we can ask. Okay, and if you heard about it, this is already known in the so-called like 3-dimensional rotation. There's a theorem called Euler's theorem in 3 dimensions. I think it's taught in classical dynamics. 就是有没有学过？就是所有的旋转可以有什么欧拉角，有3个角度。哦，如果没有，so in the okay, so there's a okay, if you don't know this, you can check Wikipedia. There's a thing called Euler angle. Yeah, okay. So you basically say that any rotation in 3 dimensions can be rotated using 3 angles, or using the z. You use the z-axis as a basically any 3-dimensional rotation can be done by using 2 different axes, 2 non-parallel axes and then you do rotation. So yeah, so simply speaking, you take any SO3, you take any rotational matrices. You can decompose these guys in 3 dimensions like Ry for some angle theta1, Rd for some angle theta2, and Rd and Ry for some angle theta2. This is the well-known result. So actually, it's not restricted to y and z. You just take any 2 non-parallel axes that you can decompose. Okay, and so single cubic unitary is basically SU2, right? So there's a local homomorphism between S2 to 1 map to SU2 to SO3 if you learn some quantum physics. So the results basically say that any single cubic unitary can be done by using the y rotation along y-axis, Pauli y, Pauli z, and Pauli y. But you need to take account of extra phase, right? So there's an extra phase. So yeah. So if you know these 3-dimensional results, then you can understand this theorem. So this theorem says that for any unitary operation U on a single cubic, there exists a real number alpha, beta, gamma, and delta. So these 3 are angles, basically z, y, z. Oh, so yeah, I use different by c, y, d. So z, y, z, these 3 angles. But notice that these are rotational, right? So they are determinant 1. So, but this is general single cubic unitary. So you need to add the extra phase to this here. So hopefully you can believe this is true. Okay. But okay, so this is decompose arbitrary single cubic unitary into a rotation and a global phase. Okay. So, but actually there's a proof for it. So I mean, if you see a textbook proof is say that you can just brute force prove it. This is not but ideal is that maybe let me just by the way, so to prove this 3-dimensional version is a non-trivial. But for proof 2-dimensional, what we know is that okay, so it's you have that 2x2 unitary, right? So it's B. And so the condition for this unitary is that the rows. So if you see this vector, right? So this is unit. This vector has been. It must be a unit vector, and this is a unit vector, and these 2 are also donut. right? So the condition must be like a squared but b squared is 1 equal to c. The length is 1, and then it must be orthogonal. So okay, so you take any A, B, C, D satisfy this relation, then you will be unit. This is the condition. You can write down the you can prove it by write down the neighbor 1. Then if you write down this, then you will see it's the same as this. Okay, so if you believe this is true, then you can parameterize this A, B, C, D. Forget about all these phase. Its magnitude can be written as rotation matrix, right? So it must be cosine sine minus sine. Okay, and after that you can just take the phase and then plug it. And once you plug this into this form, then you can prove it matches with this. So it's somehow like basically, I believe the proof is that you already know the answer, but just try to figure out the truth. 这证明就是说，你知道一个 unitary 矩阵一定要长得像，一定要长得像这个形态。所以 unitary 矩阵如果忘掉所有的 face 的话，它就是旋转矩阵 up to 一个 global face。所以你先把 global face 踢到外面去，然后所以它的绝对值一定是旋转矩阵，一定是 cosine sine minus sine cosine。And this is rotational matrices. If you forget about global face and forget about extra face, then this must be a rotational matrices, right? Two dimensions, so it's cosine sine minus sine cosine. And after that, you just add the face back. Then you can prove these results. Okay, so yeah, so hopefully you believe this is the valid proof. Okay, so this proves that what this proves saying that any single cubic unitary can be decomposed into an extra phase. Okay, one extra phase plus three different rotations dy. Okay, so yeah, I mean if you know the three-dimensional results, this should be oh, so it's easy to believe. Oh, by the way, so in the circuit model that so we're gonna draw a circuit. As we draw it draw like this way, right? For example, that this is called AND gate, and this is called NOT gate. Right. So this is simple classical circuit theory, but in content that we also draw a circuit. Right? By the way, this is from textbook. Okay, so when we draw a hot line, oh by the way, so this line is a single cubic. So one line basically is one cubic. So what is so you need to read from left to right. So that means that if there's a state here, single cubic, then you apply hot line, then you get something. And it's x gate, y gate, z gate, etc. As a compared to classical circuit theory, it's basically straightforward. Oh, okay. So now from this single cubic unitary results, then we build another theorem. Okay, so this theorem looks weird, but we all know why we need to use. So this theorem says that for any unitary U on a single qubit, there exists three unitaries, ABC, such that their product is 1, and the U can be written as exponential I alpha AX BXC. So this theorem looks very weird. Okay. 这定理就是说，你给我一个 unitary， 我可以找到3个 unitary， 它们乘起来是1，然后呢，最大的 unitary 是全部乘在一起，或中间差了2个 x。Oh, by the way, so I need to say something. So when you read this, read as equation, it's fine that you read from that to right. But when you draw a circuit, and then when you draw a circuit of this ABC. Right, let's say you want to draw a circuit of this ABC, you need to draw from left to right, right? And remember that the convention of linear algebra is that this guy actually has a matrix, so it acts on the vector to the right, So when you draw a circuit, you need to draw like this. It's not ABC, right? It's CBA because because you stay here. So this is just a small convention. 就当你算画电路的时候，你 ABC 乘上一个向量的 state 的时候，你要从左边画到右边。就你的电路是从左边看到右边的。 所以你要这样画，对不对？You first apply C and then apply A, B apply A. Okay, so this theorem is weird, but we will use but let's quickly prove it. So proof of this is just it's just simple, but so proof is that you first notice that you can decompose Q into alpha, beta, and gamma. Alpha, beta, gamma. Okay. Now you define A to be define A to be RC beta for this term, and then you split this middle gamma phase into half, right? Here, and the B is defined to be Ry minus gamma divided by RC. To be minus gamma minus delta minus beta divided by 2, and there extra C for RC delta minus beta divided by 2. So decompose into 3 of them. It looks a little bit difficult, but let's first check that if you take ABC, then you get RC beta here, but you get Ry gamma divided by 2 here, and you get there's our minus gamma divided by 2. And then for RC terms here and RC terms here. So if you do this, you can see that these two terms cancel. And these two terms so these two terms give you extra minus beta, which is cancel with this. 对，大家看到没有？比如说，你现在把 A 选这样，把 B 选这样，C 选这样，大家会觉得复杂，不知道我在做，我给他知道。你现在把 A、B、C 这样子想 ，once you try to A、B、C, then the middle these two terms will cancel, and then these two terms will give you the extra minus beta, which cancel with the first term. So you get A, B, C equals to 1. Okay, and okay. So this is the first condition that we have proved. Now let's say since x squared, Pauli x squared is identity, and so we can try to. So the next thing I want to claim is that if you insert x in the middle of A, X, B, and C, then you will get this original vector. Okay. Why this is true? Remember that x and y are in that confused, right? So there's a okay. So let me just write it. So what simple to prove in the following, right? If you take x times any ry here, the x, you conjugate x with y, and you know x and y are anti-commutes, right? So this will give you the extra minus sign here. Okay, so we can prove this by using it's basically an elementary proof, or you can prove it by using so-called Baker-Campbell-Hausdorff formula. Let's see. Okay, so because you know x and y are anti-commutes, right? So any algebra generated by y is there's extra phase here, extra minus sign here, right? So to evaluate this guy, then you just apply this formula on B. So let me just do it for you. So okay, so let me just write out. So this is A. Okay, so maybe you don't know why we need to prove this weird theorem, but the reason will be clear after these slides. So this is X. Z minus. Okay, so we want to evaluate this, right? This is A, B, C. Compared to the right? So in order to evaluate this, you just insert x here. You insert x here, right? Because x squared is 1. So you can insert x in the middle. And so this guy, using this formula, will get Ry gamma divided by 2. And this guy will get Rz. You just get extra minus sign, you get delta plus beta divided by 2. Right, so you combine everything. So this is a magic. Okay, so you can see the magic for Z. This is beta phase, and these are Y and Y, right? So these are gamma divided by 2, gamma divided by 2, combined become gamma, become a single gamma. And for these two, this delta is the same, but beta cancel, right? So you get RZ delta. So you get C with beta, Y with gamma, Z with delta, which is beta, gamma, and delta. And with X suffix. So finish it.听起来很复杂。Okay, so if you forget, if you don't know the details, fine, but you can go back there, go home, check it. So the idea is basically, you take any single unitary, I can decompose with 3 matrices ABC 1 and AX, BX, C. Decompose this unitary into these 3 mirror matrices. Alright, so just remember this theory. Okay, so let's talk about the 2QP unitary. Because so now we already showed that single QP unitary is good, right? I can use elementary R. I don't need to do any single QP unitary. I only need to do like rotation along Y, rotation along Z, and then with a global phase. That's 3 are enough. Actually, they are infinite because the angle can be arbitrary. But this is the problem that we will solve later. So let's talk about 2QB unitary. 那刚刚的意思是说 single QB unitary 是可以很简单的解决，因为我们只要有2个转轴加上一个 phase 就搞定。但是现在是所以我们接下来就面对阿大陆2个 unitary. Okay, so before we go to like general 2QB unitary, we will talk about a simple 2QB unitary called control unitary. Or control unit. So this control unitary is similar as a classical so it's similar to the classical so-called NOT gate, but it's basically the control one. So the idea is that so-called control operation is that if a control qubit, there's a qubit called control unit. If the control qubit is true, then you will apply another unitary. You will apply another single qubit unitary on the target. So this is the very small subset of the 2QB unitary. Right? Okay, so you only need to know one control qubit unitary called the control NOT. Or basically it's the most important one called C-NOT gate. Okay, so I will only talk about the definition. So this C-NOT gate says that there's so now you have 2 qubit, right? So the definition is very simple. It says that if the control qubit is 1, then you flip the target qubit. 就是你现在有这就是so this is you can do this as a simplest 2 qubit unitary. This is very simple as you write code. Right? So what this definition say that this C-NOT gate is a 2 qubit unitary. So if you draw it, you need to draw 2 lines, right? And this is the convention, which is black dots compared with this O plus. So what this means, this is a control. This is called top target. If the input is 1, then you need to split the target. Okay, so you can write the matrix representation as this. Okay, or you can write the vector form as If the input state is 0, 0, then it maps to 0, 0. Because the first qubit is 0, right? So if it's 0, 1, it maps to 0, 1. Right? But if it's 1, 0, this guy is if I apply C naught here, C naught on the if the control qubit is the first qubit, then this one should you will flip the second one. 1, if 1, 1, then now 1, 0. And if you write it as a matrix representation, these two are the same. These two will flip. So this is why you write in terms of matrix. This is 1, 1, 0, 1, 1, 0. Okay, so hopefully this matrix will match. Matrix form match with the definition. Okay, so so you can say that but why? So let me see. So one can view this control NOT gate as described as if the first qubit is 1, then apply X gate to the second qubit. Because the poly X basically is split gate. Right? The X map is equal to 1, or 1 to 0. And the X gate, the X is just 0, 1, 1, 0. So this is X, right? So you can say, all right, then I can define any general control operation U as this. For a single qubit unitary U, I can define a control U gate X like if the first control is target, if the control is 1, then I apply the U on the target. Okay, so pictorially, then this is what people use. Hopefully the definition is clear, right? So what this red dot connect means that these guys are control guy, right? This guy will control this qubit. So if this guy, if the input is 1, then apply U. Okay. So you might say, oh, so I have a control U, right? Okay, so now there's a non-trivial theorem. How can I implement control U for arbitrary U? So notice that U is a single qubit unitary. Okay, so what these theorems say that you don't need to implement control U gates. You only need the C naught gate plus arbitrary single qubit unitary. Then with these two combinations, then you can implement any control U. So you know what these theorems before. You know what this theorem says. So we are interested in control U, a special case of two qubit unitary called control U. Like control U means that there is a control qubit. If the control qubit is 1, then I will apply the single qubit unitary U on my target. But how can I do this? So this theorem tells me that you don't need to have any control U. You only need one special control guy called control NOT. Once you have this control NOT with arbitrary single unitary U, then you can combine it to this control U operation. Okay, so the goal is to implement control U for arbitrary single unitary U using a single qubit operations and C naught。这个定理的意思是说，其实你只要 C 纳就可以了，你不用 control 任何的东西，你不用其他的 control。So the theorem proof using this weird decomposition that I just proved it before. You take U, there exists three unitaries, A and B and C, which produce 1, and you can U is expressed by this ABC with inserting with X. Okay, so it's like very weird. How can someone prove this? Okay. So before we prove it, let's talk about this is a simple lemma called control phase shift. Okay, so what is phase shift is very simple. So suppose you want to do a control phase shift. So what this control phase shift means is that if the target is 1, then I apply extra phase disclosure I alpha apply on the second qubit. Right? So actually it's very simple, 0t, map to 0t, because this guy is because if this guy is 1, then I apply disclosure I alpha 1. Okay, so for circuits, you just apply 0, 0 to 0, 0, 0, 1 to 1. For 1, 0, then you get extra phase. 1, 1, you get extra phase. So pictorially, it's just this. You control you control with a face. But weird thing is that this guy is not this matrix no control here. This guy is actually here. You just apply 1, 0, 0 exponent I alpha on your single qubits, then tensor product is the same. This will be the same. Hopefully it's okay. Then let me just quickly write down. It's not difficult, but this. Oh, it is. Okay. Why? Okay. So to prove these are the same, right? We only need to prove on. Okay. So to prove these two matrices are the same, we only need to prove it's the same on the basis. Okay. So from the left, that we already defined, right? It's which is simple. That I just write down. For the right one, what this mean? What this means? So, let's say this applies to alpha 0 plus beta 1. As a matrix, what this means that you get alpha 0 plus exponential I alpha beta 1. Good. Okay, so let's say for a second qubit, let's say gamma 0 plus delta 1. So if you tensor product with these two, so you get finish it. So okay, so this is the first qubit, right? So if you apply this I1, 0, 0 exponential I alpha on the first qubit, so let's say the first qubit is alpha 0 plus beta 1, then it becomes like alpha 0 plus beta 1, but there's extra factor here, exponential I alpha. Right? So this is the state after this single qubit unitary. But let's say the second qubit now is this gamma 0 plus delta 1, right? So the total state will be a tensor product, because we just take the product. So you get for 0, 0, you get alpha times gamma, right? And then for this 0, 1, you get alpha times delta. So these two are the same. But when the first qubit is 1, then you get extra exponential I alpha, right? So you get exponential I alpha beta gamma 1, 0, and exponential I alpha beta delta 1, 1. So that means that if you see this equation, that means that if the first qubit is 1, then you will get an extra phase. Then this is exactly the same as the left-hand side. Okay, so left-hand side says that, oh, if the first guy is 1, then you need to add an extra. So what this phase shift tell you that, oh, if you see the control phase shift, that is basically you don't need to care about, you can just destroy this guy, move into the second qubit. So this is the lemma. Okay, so once you prove this, then this is the theorem. So this theorem says, okay, so now if you want to do any control unitary view, why is it going unitary here? You can decompose it into this to the right hand side. We first apply your theorem to the you just decompose your U in terms of this guy, ABC equals 1, and decompose, and you add a phase here, and in the middle one, then you insert with the loss of C naught, and you get you just write CA. Okay, so it's clear that this is true, but let me just write down. Let me just this is a simple answer, but let me just prove they are the same. 大家懂我说什么？大家懂我说，就是说你要 apply single qubit unitary，你要 apply 任何的 control u 的时候，你可以用这个定理把这个 control u 分解成小小的 single qubit，所以你加上 C naught。So what the whole point of this theory is that you don't need arbitrary control U. You only need control not to independently control U. Okay. So let me just quickly prove it. The proof it is one is so one is let's see. Okay, so I want to prove they are the same. How can I prove? Okay, so we prove on the basis, right? So let's say if the so you need to read from left to right, average. So if the if the control qubit is 0, then the left hand side will be identity, right? Because there's no U here. And from this side, if the input is 0, then there's no C naught here. There's no C naught here. So for any state below, for let's say this state side, right? For any state below here, the left hand side is identity. And the right hand side, you will apply C and apply B and apply A. Because there's no control if the first qubit is 0. Right? So mathematically you just apply C, apply B, and apply A. Right? And this is identity. By definition, because the 3 of ABC, prove out ABC is identity. Good. Okay. And okay, so this is the case when the target qubit is 0. After the control qubit is 0. If the control qubit is 1, the left hand side will implement U, right? Will implement U. And the right hand side, now if the control is 1, then there will be extra X here because it is C naught, right? You apply X here and apply X here. So the total effect will be you apply C, then X, then B, then X, then A, and the extra phase. So we use U. All right, so finish. 这个大家可以看用眼 ，OK， so or you can just view it all. If it is 0, then it's identity. But if 0, then you apply A, B, C, which is 1. And if the control is 1, left hand side is U, and the right hand side becomes A, X, B, X, C with extra. Okay. So what this theorem tell you that you don't need to use for 2 qubit control U, you can use you only need the control not. So this is the so now you can see our framework, right? There's many different unitary here, but now we build small decomposition theorem on each small on each part. Okay, so now I want to convince you there's a okay. So one can also define a multi-qubit control operation, which is much more like complicated. What this theorem what this multi-qubit control is meaning that you can define more general thing. You can say, oh, I take K to be unitary U, and I can define a multi-qubit control, meaning that if the first n qubit are all 1, then I will apply a unitary K to be unitary on the best of K qubit. 这个意思就是说，我希望可以定义说，我可以再定义更复杂的 multi control。And multi control meaning that I can say that I can have more conditions and say, oh, if the first n qubit are all 1, then I can apply my K to be unitary on the best case. These are more general than one can define. And the special case is so-called this Huffley case. So this Huffley case basically flip the target qubit if 2 control qubits are 1. So this Huffley case are like 3 qubit gates. If the first 2 qubits are all 1, then it will flip the third qubit. Okay, so you can say, oh, I can. Then how about this multi-qubit control operation? And the theorem say that you can get any if you have C naught, then you can do it. Okay. Okay, so for example, let's say n equals to 4 and k equals 3, right? You can define more general control U like this. Let's say 1, 2, 3, 4. So what this pictorial means that if 4 of these guys are all 1, then you can apply the three cubic unitary apply on the rest of it. You can say, oh, I can define this. But can you decompose this into a more elementary one? Okay, so this is some non-trivial proof. Okay. This proof is non-trivial, so let me just skip here. Okay. Okay. So now, so this is done by some people. Can figure out that in a special case, let's say you have two control and single to be U, and if you can find the matrix B, which is squares U, then you can somehow like magically decompose this guy into this. This is people that spend a lot of time to figure out what. So these are you have that two control, right? But now at the right hand side, you only need the C naught and the single digit control. And then you can use the previous theorem to decompose this single qubit into the space with C naught. Now you can decompose this guy again using the previous theorem for arbitrary B. Okay, so this is just a special case. But okay, so the main goal of the rest of the lecture is to show that if you have C naught and single qubit unitaries, for arbitrary single unitaries, then this would enough to get you the whole n qubit unitaries. So this is the very non-trivial theorem that people just invented, but I believe it's 30 years ago. So it's amazing that you have any n qubit unitaries. These any n qubit unitaries can be decomposed using arbitrary single qubit unitaries plus 1 2 qubit unitaries, which is control now. 听起来这个听起来很神奇啊！就是说，你任何一个巨大的 unitary， 其实只要你有 control not 加上这些小小 single qubit unitary， 就可以把所有的构。所以其实你只要 single qubit 跟 two qubit unitaries 就能做任何的大的 arbitrary n qubit unitaries. So to prove it, we need some time. But let me see how can let's see. Okay, so the goal is to prove this, right? So to prove it, let's first there are a few stages, right? The first stage is that how can we implement control unitary or so the goal is to let's forget about the whole theory. Let's say we only need to hope to implement arbitrary control U, but let's say let's consider U to be single qubit unitary. So remember that we proved there's a case that n equals to 2 that spend some time to figure out. But the theorem say that we can do for arbitrary n with using the single qubit gate and C naught, and there's extra so-called Toffee gate. So Toffee gate, let's say this that you will flip the third qubit if the first two qubits are 1. Okay, so this proof is mathematical is hard to write, but let me just do one example for you. Okay, so now we use the example as proof. Because the proof is complicated, but let's focus on let's say n equals to 5, and so this n equals to 5 basically means that if the first 5 qubits are all 1, then I will apply U on the 6th qubit. Okay, so you can compose n equals to 5 using this equation. Okay, so here, right? So let's say these two are let's say these 5 are all 1, right? And if 5 are all 1, then the idea is that we add the extra 4 work cubic here. So let's say if 5 of them are all 1, then basically you will flip all the working cubics to be all 1. Because these will come, these are complicated. If these are all 1, then this will be 1. Then these are 1, then will flip. So all the working cubic will be 1. Then the target qubits, then they will apply the well, I'll say if these two are 1, then this case then this will be 1. But this third one but there's another complication here. So if these are 1, then these are 1, then this will be 1, then all the 1s will pass into the final gap. So what I'm saying is that if this guy is 1, then if only if all of 5 are 1. If there is a single C which is not 1, then there must be some working group which is not 1. So basically, you went,
Yes, and what are the 5 connections on the right hand side doing?
Yes.
Yeah.
So what this means is that you need to like undo the operation from that.
So how we are reading this scheme is from left to right and not from up to down.
No, just from left to right.
Okay.
Yeah. So
yes. So
if I can, I should try to like write on the. So what this means that or I can do the reverse. But let's say this guy. So I'm going to do the reverse. Let's say U is a 5. So this guy is 1. So if this guy is 1, but this guy is 0. So that means that if this guy is 1, then this guy is 0. That means that this top gate has been activated. And if this top gate is activated, then this guy must be 1, and this guy must be 1. So C5 must be 1. So this must be 1. But if this working qubit is 1, then meaning that this is 0, but meaning that these top gates are also activated. So that means that C4 must be 1. And you know C3 must be 1, C4 must be 1. So this is true. So what these results tell you that originally which is 5 qubit control 1 qubit. But this decompose tell you that you only need top gates, which is 2 qubit control 1 qubit. Then you're done. Then it's done. So what just right now. About this purpose, multi-stage. So it says that if I apply which is single U, then I can decompose into like C2U. So C2 copy gate. So I just need a copy C but single U. Okay. But previously, I tell you the magical results is that for any C2U, C2 control U, you can decompose into C naught. So this also divided by C naught plus some single U. Remember, theorem. These weird results. These weird results tell you that for the top limits, you just apply U equals X. There's a decomposition for this.
Is the unitary matrix always?
Yeah, remember it's 1. The absolute value of the equation 1.
And you always find the such.
Yeah. So the reason is that this unitary is always diagonalized, right? Because it's normal matrices. So you can always write you can always write as this. Or another unitary.
Yeah,
you take a square root. Okay. So yeah. So Okay, so what we have done? The first thing is that single cubic unitary interface plus three rotations, measures three rotations, x and y and z. And any control apply on single unitary, then we are all using C naught and single cubic unitaries. Okay, so now with these two powerful method, then we can deal with arbitrary to the text to the unitaries. Okay. Let's see. Oh, maybe we'll take a 10 minutes break. We can go back to the